friends, dear learners and my dear student. First of all, I welcome you on the lecture Ultraviolet Visible Spectrophotometry. I am Dr. S.R. Labhade, working as Associate Professor in the Department of Chemistry. Student, in previous lecture we discussed the instrumentation and working of single beam photoelectric colorimeter, instrumentation and working of single beam spectrophotometer, and instrumentation and working of double beam spectrophotometer. In today's lecture we discuss simultaneous determination of two or more components present in the mixture. If two or more components present in the mixture that absorbs electromagnetic radiation at separate wavelength, then their determination is possible by means of BS law or by spectrophotometry. There are some conditions for simultaneous determination, and number one, conditions for simultaneous determination. The components present in the mixture should not react with each other. That means there is no chemical reaction in the components of the mixture. Second thing is that each component show its absorbance at separate wavelength. Third component, third requirement, each component should absorbs independently in the mixture. Fourth component, lambda max value or wavelength of absorption that should be differs widely. Lambda max value should differs widely. And fifth component, epsilon, that is the molar absorptivity of each component remains same in the mixture. If the mixture containing two or more components and each component should absorb independently where there is no chemical reaction and lambda max value of each component differs widely and epsilon value that would be remains same in the mixture, then we can simultaneously determine these two components present in the mixture. Simultaneous determination is done by means of two different methods. First method is called as by using a isobestic wavelength. Isobestic wavelength is the wavelength at which two or more components have same absorptivity. Isobestic wavelength in which which two or more component in the mixture have same molar extinction coefficient, or epsilon value. Then we can also determine two or more components simultaneously. Now what is this isobestic wavelength? Isobestic wavelength is identified by means of absorption spectra. Suppose this is the absorption as a function of wavelength. This graph is called as spectra. In a spectroscopy, a graph of absorption or transmittance as a function of wavelength is called as spectrum, and therefore technique is called as spectroscopy. Suppose, for example, we have a two-component system. For example, this is a first component, and suppose, for example, this is a spectra of second component. Here, this is a absorbance. Here it is 0. It is increases like this. That means here this is a wavelength, or this is a lambda, where these two components have same absorption value. Concentration of both solutions are same. If absorbance is same, then that wavelength is called as isobestic wavelength. We can utilize this isobestic wavelength for measurement of the absorbance of two components simultaneously. Now in this spectra, here both components shows absorbance at lambda I. We can say lambda I. And here this is the wavelength at which a component B does not show absorbance, but component A shows absorbance. Therefore, here at epsilon A, at isobestic wavelength, whatever the absorbance thus obtained is equal to or is directly proportional to the concentration of component A and component B. While absorbance at lambda A, this is lambda A, is equal to the absorbance that is directly proportional to concentration of A only. And therefore here, when we measure the absorbance at isobestic wavelength, then we have concentration of both components. Therefore this absorbance is proportional to concentration of A and concentration of B. But absorbance at this wavelength, that is related with the concentration of A only. Therefore, when we measure the total concentration at isobestic wavelength and concentration of A at its lambda maximum, by subtracting the concentration of A by determining it at this wavelength, we can find out the concentration of B in this case. That means here, simultaneous determination can be carried out by using a isobestic wavelength. Students, we discuss the second type of simultaneous determination, that is based on additivity of absorbance. This principle permits us or allows us to subtract the absorbance of blank solution from the sample solution Similarly, this also allows to determine the spectrum of a component by subtracting the absorbance of another component Suppose for example we have a two component, and these two components, suppose this is a absorption spectrum of two components in this way, and here this is a component A, or suppose component X, and this is component Y. We have to find out the absorption spectrum of Y. Then we can find out first upon the absorption spectrum of pure A. The absorption spectrum of pure A is like this. This is a pure A. Then here this is a mixture of A and B, pure X. Then absorption spectrum of this X can be determined, that is by subtracting this absorbance from this. We have here the absorption spectrum of component B or Y. In this case by subtracting absorbance of pure X from this mixture X and Y, we can have an absorbance spectrum of Y. This is allowed by the additivity absorbance principle. That means it allows to subtract the absorbance of blank solution from the sample solution. Blank solution means the solvent components or other reagents. Their absorbance we can eliminate it from the sample solution by subtraction method. As well as by this subtraction method, we can also obtain the absorption spectrum of another component. Suppose for mixture we have this absorption spectrum, and we have absorption spectrum of pure compound 1, or one compound have a absorbance. Then component second, its absorbance and absorption spectrum that can be determined. Therefore, here this principle also allows to subtract the absorbance of one component from the another if those are present in the mixture. And therefore, we can utilize this for simultaneous determination of two or more components present in the mixture. According to Beer's law, we know that absorbance is directly proportional to concentration. That means absorbance is directly proportional to number of absorbing species present in the solution. Or we can say that absorbance is directly proportional to number of absorbing components in the mixture. Therefore, here total absorbance of the mixture is the sum of absorbance of two or more components. And therefore, here we can write total absorbance is equal to summation of absorbance of I component, I from 1 to n. Therefore, is equal to summation of epsilon I, that is into B into Ci, I from 1 to n, or which is equal to B is 1 centimeter, or it is constant for measurement. Therefore, it is summation of epsilon I into Ci, I is equal to 1 to n. Therefore, here in this case, the additivity of absorbance principle allows to measure the total absorbance of n component present in the mixture. That is summation of all absorbance of all component, and therefore here this B is 1 centimeter. And therefore, for that all components here, the product of molar absorptivity of each component and concentration of each component. Therefore, this total absorbance can be measured as a epsilon I into Ci, where I from 1 to n. In this way, here additivity absorbance principle allows to determine the total absorbance. Therefore, in this case, that is A is equal to A1 plus A2 plus A3 plus AN. According to this equation, total absorbance is equal to absorbance of first component into absorbance, plus second plus third plus absorbance of nth component. And therefore here total absorbance A is equal to here epsilon of first component into B into C1 plus epsilon 2 B into C2 plus epsilon n into B into Cn. And therefore, as B is 1 centimeter or B is constant, therefore we take B common here. Therefore, epsilon first into Ci, C first, plus epsilon 2, C2, plus epsilon n, Cn, and like this. As B is equal to 1 centimeter, therefore total absorbance is equal to epsilon of first into C1 plus epsilon of second into C2 plus epsilon of third plus into Cn plus epsilon of nth component into Cn. In this way, the total absorbance that can be determined by means of this additivity principle. Therefore, total absorbance is the sum of epsilon of first component into concentration of first component plus epsilon of second component into concentration of second component plus epsilon of nth component into concentration of nth component. In this way, this additivity principle we can apply it for measurement of absorbance of two or more components, and if these components do not react to each other, that have well separated lambda max value, then we can easily determine their concentration by means of Beer's law. If the molar absorptivity that is epsilon is maximum at lambda max, then we can say it is at an epsilon max, that is maximum molar absorptivity at lambda max. And therefore here in this case, the additivity absorbance principle can be applied for determination of two or more components. For example, we can consider the two component system. In this case, suppose we have component first, its lambda max is lambda 1 and its concentration is C1. Component second, we have its lambda max as a lambda 2 and its concentration as a C2. Then we can utilize this molar absorptivity and concentration of both components for the determination of concentration of any one component in the mixture. Therefore, we can here discuss first of all we discuss here the procedure for the simultaneous determination by means of additivity of absorbance. For here we have two component system. We have two component system. That means we have to determine two components simultaneously. For this purpose, procedure first upon the standard solutions of various concentration of the two components are prepared separately. That means here, suppose for example we have KMnO4 as a first component, K2Cr2O7 as a second component. Then we have to prepare the standard solution of KMnO4 and standard solution of potassium dichromate having various concentration ranges. Suppose for example 0.1 moles per liter, 0.2, 0.3 to 0.6 moles per liter, so on. Similarly, we can prepare the standard solution of potassium dichromate solution also. Second thing is that after preparation of standard solution, the lambda max, that is a wavelength of maximum absorption, lambda max for both components are determined by using any one solution, because lambda max is independent on the concentration of analyte. That means here, if we have a 0.2 molar solution, that will be absorbed at same wavelength, 0.4 molar solution, that will again absorb at the same wavelength. Therefore, any one solution that can be selected for determination of lambda max. When we determine the lambda max of each component, then absorbance of all standard solutions are measured at the lambda max of each components. At their lambda max, absorbance of all standard solutions, means standard solution of potassium permanganate and standard solution of potassium dichromate. If potassium permanganate have lambda max 540, we have to measure the absorbance of all these solution at 540. If lambda max for potassium dichromate is 440, then we have to measure the concentration of all these solutions at 440 nanometer. And therefore here absorbance of all standard solutions are measured at the lambda max value of each component. Number 4, then a graph of absorbance as a function of concentration is plotted for each component. Then number 5, the slope of each curve, that is calibration curve, is determined, and here the slope is equal to, as A is plotted as a function of C, slope is equal to epsilon into B, since we have a straight line passing through the origin. That means here, this is the equation of straight line, that is A is equal to epsilon into B into C. Here epsilon B is slope, therefore it is the equation of a straight line passing through the origin, and epsilon b is slope. When b is 1 centimeter, then slope is only epsilon. That is, slope of each component is determined. After that, here by this absorbance of mixture is determined. That is, mixture is here. For example, we have a KMnO4 plus K2Cr2O7. Absorbance of mixture is determined at both lambda max value. That means at lambda max of this and lambda max of this, we have to determine the absorbance of the mixture. Then by means of a simultaneous equation, we can determine the concentration of here component first and component second in the mixture. Therefore, here in this case, suppose for example, here we have two component system, then absorbance of mixture at lambda 1, any wavelength, that is additivity of absorbance stays that absorbance of first component plus absorbance of second component, absorbance of first component at lambda 1, absorbance of second component at lambda 1. Therefore, total absorbance at lambda 1 is equal to epsilon of first component into concentration of first component at lambda 1 plus concentration and epsilon of second component, and it is measured at first wavelength, that is lambda max 1. Similarly, here absorbance at lambda 2. This is absorbance at lambda 1. Therefore, at lambda 2, total absorbance is equal to again absorbance of first component plus absorbance of second component at lambda 2 is both absorbance measured at this lambda 2 wavelength. Then again here a lambda 2 is equal to here epsilon 1 into C1 at lambda 2 plus epsilon 2 into C2 at lambda 2. Call this equation number 1 and this is equation number 2. If we solve equation 1 and 2 simultaneously for determination of C1 and C2 as a concentration of first component and concentration of second component respectively. Therefore, directly we can have here C1 is equal to concentration C1, concentration of first component C1 is equal to, therefore C1 is equal to epsilon 2 at lambda 2 into absorbance at lambda 1 minus epsilon 2 at lambda 1 into absorbance at lambda 2 divided by epsilon 1 at lambda 1 into epsilon 2 at lambda 2 minus epsilon 2 lambda 1 minus epsilon 1 at lambda 2. Therefore, in this case, here this gives the concentration of first component. Similarly, C2 concentration of second component the concentration of component second can be determined as an epsilon 1 at lambda 1 into absorbance at lambda 2 minus epsilon 1 at lambda 2 into absorbance at lambda 1. Denominator value are same, that is equal to epsilon 1 lambda 1 into epsilon 2 lambda 2 minus epsilon 2 at lambda 1 minus epsilon 1 at lambda 2. This is equation number 4. Therefore, equation number 3 and equation number 4 can be utilized for simultaneous determination of concentration of two components in the mixture as a C1 and C2. In this case, epsilon value are obtained from the graph, that is a compound is in a pure state and absorbance is taken from the mixture. The step which is given in the procedure of simultaneous determination, that is when we plot a graph of absorbance as a function of wavelength, then we have this graph like this. At lambda 1, the graph is like this, where first component shows maximum absorbance. Therefore, here this is for first component this is a calibration curve. For second component, this is a calibration curve. We can determine the slope of this line, that is epsilon of first component at its own wavelength, that is lambda 1. If we determine the slope of this line, that is equal to epsilon 2 at lambda 1. Here A1 and A2, that is this A lambda 2 and A lambda 1. For this A lambda 1 or A lambda 2, that is obtained when we test the mixture at lambda 1 and lambda 2. Therefore, similarly we have this calibration curve at lambda 2. Therefore, at lambda 2 we have this curve and we have this curve. This is for second component, this is for first component. This is because of each component absorbs maximum at its own wavelength. Therefore, at lambda 2, second component shows maximum absorbance and another component shows minimum absorbance. Therefore, in this case, this slope is equal to epsilon 2 at lambda 2 and this is a slope equal to epsilon 2 at lambda 2. Sorry, epsilon 1 at lambda 2. That is absorbance of first component at the wavelength of another. Therefore, these two calibration curve gives us a value of epsilon at different wavelength, and then we can utilize this absorbance value for determination of concentration of component first and second by using these two equations, C1 and C2. Student, we solve one problem based on this. Calculate the concentration of KMnO4 and K2Cr2O7 in the mixture using following data. Here, concentration of solution lambda 1, that is 540 nanometer, lambda 2 as 440 nanometer, where K2Cr2O7 shows maximum absorbance. Here KMnO4 shows maximum absorbance. Concentration, that is 1.0 into 10⁻³ moles of KMnO4, and here concentration is 1.0 into 10⁻³ moles of potassium dichromate, and this is a concentration, this is a for a mixture containing both potassium dichromate and this potassium permanganate. Therefore, absorbance of the absorbance of this solution at this wavelength is 0.48. For this potassium dichromate it is 0.05. Absorbance of KMnO4 at 440 is 0, and at this wavelength it is given as a 0.28. Here mixture 0.76 and here 0.28. 38. This much information is given to you, that is, this concentration of potassium permanganate having absorbance this much at 540, it does not absorb at 440. Therefore, this is the concentration of dichromat, its absorbance at this wavelength. For this, its absorbance at its own wavelength, and this is the absorbance of mixture at both wavelength. Using this data, we have to find out the concentration of potassium permanganate and concentration of potassium dichromate in the mixture. Here we consider KNO4 first component and its concentration C1. Then K2Cr2O7 as a second component and its concentration C2. Therefore, first of all, we have to find out the value of epsilon for both components. Therefore, epsilon of first component at its one wavelength lambda 1, that is equal to A upon C, which is equal to 1.0 into 10 raised to minus 3 divided by, it is equal to 0.48 divided by 1.0 into 10 raised to minus 3, which is equal to 480 liter per mole per centimeter. Similarly, epsilon 1 at epsilon 2 means at this wavelength, that means at 540 for second component, that is again A upon C. Concentration absorbance is 0.05 divided by 1.0 into 10 raised to minus 3. It is 50 liter per mole per centimeter. Similarly, epsilon 1 at lambda 2 is equal to A upon C, which is equal to here 0 divided by 1.0 into 10 raised to minus 3 means 0 liter per mole per centimeter. Similarly, epsilon 2 at its own wavelength lambda 2, again A upon C, which is equal to here 0.28 divided by 1.0 into 10 raised to minus 3, which is equal to here 280 liter per mole per centimeter. Therefore, here we have epsilon value at 4 different wavelengths. Therefore, here epsilon value is, for this is 480, for this it is 0, epsilon 1, this is epsilon 2, epsilon 1 at lambda 1, epsilon 2 at lambda 2, epsilon 1 at lambda 2, this is epsilon 2 at lambda 1, and this is epsilon 2 at lambda 2, 280, here it is 0. Therefore, we have, here 0.50, here we have all these value of epsilon and absorbance of mixture. Then we can find out here the C1 and C2. Therefore, C1 is equal to, here C1 is equal to concentration of first component, C1 is equal to epsilon 2 at lambda 2 into constant absorbance at 1 minus epsilon 2 lambda 1 into absorbance at lambda 2 divided by here epsilon 1 lambda 1 epsilon 2 lambda 2 minus epsilon 2 lambda 1 into epsilon 2 lambda 2, that means here 280 into 0.76 is minus 50 into 0.38. Therefore, divided by here 480 into 280 minus 50 into 0, When we solve this, we have this C1 is equal to 1.44 into 10 raised to minus 3 moles per liter. That is the concentration of KMnO4, because we consider that as a first component. Similarly, here we can find out the C2, that is concentration of second component. C2 is equal to, here for C2, here epsilon 1 lambda 2 epsilon 1 at lambda 1 into absorbance at second wavelength into epsilon 1 at lambda 2 into absorbance at first wavelength, and all other components are same. Therefore, we can here C2 is equal to 480 into 0.38 minus 0.0 into 0.76 divided by, these values are same, 480 minus 480 into 280 minus 50 into 0. When we solve this, C2 is equal to 1.357 into 10 raised to minus 3 moles per liter. This is the concentration of potassium trichromate. Therefore, in this way, additivity of absorbance principle can be utilized for determination of concentration of C1 and C2, that is a two component system. Student, with this we stop here. Thanks for joining me. Wish you all the best. Keep learning. Happy learning.